Hello everyone. So my name is Umut Demirbozan, and today I'm going to talk about the stabilizing the principle of DES-Y3 superstructures with my collaborator and supervisor Shashad Redator from University of Portsmouth and Ismael Ferrora and Pablo Fosalva. So I'm a PhD student at IFAE in Barcelona. I am in my last year right now. So I am in the thesis period, and this is the paper that I authored for most of my thesis, and I'm gonna explain about it. So the study is already on arXiv. You can see. So there are more details in the papers, of course, if you want to check. So this is the arXiv number there. And you're welcome to comment or send me a message privately if you're interested. So I'm going to give a brief outline what I'm going to talk about in this presentation. First, I'm going to explain previous void cross CMB studies, a little bit of background, and then I'm going to explain what CMB lensing is, and then explain what cosmic voids are, and a little bit about information about the dark energy survey, the data I'm using, and the simulation, n-body simulation called my simulation. And then I'm going to describe my methodology and match filtering, the filtering we use for CMB maps. And then we have error analysis and covariance estimation. And then I'm going to share my results and talk about the future. So if I want to summarize the study in like one paragraph, one sentence, we use a double approach, meaning that we use Voxel void finder and also 2D void finder. I'm going to go into details in a minute. And also inverted 2D void finder to find 2D superclusters to our RCD more robust and measure the CMB lensing imprints of DES-Y3 superstructures. So these are the superstructures found in DES-Y3 dataset. And then we compare with ΛCDM expectations coming from mice embedded simulations. So this is what I'm going to mostly talk about. So now the background. So the background is there are some already published studies by cross-correlating voids and stacking void positions on temperature map, CMB temperature map, length temperature map, and detecting ISW signature, which is the second derivative of gravitational potential. So in this study, AISW, meaning that ΛCDM expectation is 1, detected in some studies a little bit higher. However, in Nadatur and Critenden in 2016, the ISW signal, AISW was close to 1. So there are some excess signal from mostly large voids and claimed in BOS and SDSS with some error bars as you see in this figure. So there is no consensus in this, because there's also another study, Hang et al., Imaging Legacy ADR8, and it shows a good agreement with ΛCDM. They couldn't really detect ISW signal, but in ΛCDM, you barely detect ISW. So Nadatur and Critenden basically agreeing with ΛCDM expectations, also Hang et al., Imaging Legacy ADR8. And also, I'm going to quickly pass this. There is Raghunathan et al., where they checked BOS spectroscopic voids and they were CMB lensing imprints by using different binning to voids. And their lensing amplitude, AL, here was measured. It was also good agreement with ΛCDM prediction. So there was no excess or weak signal coming from Raghunathan et al. And one thing interesting is that they defined a match filtering method that I'm going to explain now. And I use exactly the same match filtering method as described in Raghunathan et al., but I apply it to DES-Y3 voids instead of BOS voids. So basically, this study constitutes the basic approach, filtering approach that I'm using. So CMB lensing. CMB lensing is, okay, I'm just going to do my video. The CMB lensing from ratio 1100, when the CMB photons travel to us as the universe expands, they are disturbed by matter, And the CMB lensing is the information which is measured by kappa by distorting the CMB images. And we have quadratic estimators. This is, by the way, over-exaggerated. We can construct a kappa, meaning that we have the convergence field in that location in the sky. And that actually corresponds to matter over densities integrated along the line of sight to our max. Our max means the surface of last scattering, and from our position. Basically, it captures all the information, integrated information, projected information on the sky from that direction. And here, this delta is the overdensity on that direction. And this is mostly not known exactly. So we have an integrated information with the matter. And then Planck survey provides a kappa map. So kappa is a dimensionless quantity and also depends on the H0 and omega m. So one thing is CMB lensing that its kernel, it's the power, it's mostly sensitive to structures around roughly around 1.5 to 2. So the kernel peaks around 2. That means it is sensitive to high ratio, but in low ratio, we also detect it because we cross-correlate with voids found in 0.2 to 0.8 mostly. That's our range in direct energy survey, and can be used as an external tracer to cross-correlate with galaxy surveys. And there are some studies detected, measured sigma 8 by cross-correlating with galaxy density maps. So in this study, we're going to cross-correlate CMB lensing map, this convergence information, with the largest under densities found in galaxy distribution provided by dark energy survey. So the regions called voids, they are lack of galaxies. So as you can see here, this is just a basic representation. And they are supposed to, they are supposed to imprint a negative kappa signal, because the matter is not lens in the void, but outside of the voids, since voids density is much less than a mean density in the universe, and their volume is much larger. So they are supposed to imprint negative kappa signal instead of superclusters, which imprint positive signal. But it's important to mention that one structure, one supercluster or one void, we cannot detect its signal on the CMB. That's why we need to stack many void positions on the CMB together to increase our signal to noise. So on average, many voids stacked together should imprint negative kappa signal, negative convergence, because they represent a lower density region in the universe. So we use a couple of different void finders, 2 different void finders. One is Voxel void finder. Here, local minima in the density fields. Sorry, I think I should, yeah. So we first time detect the CMB lensing invert of Voxel voids. These are based on older watershed algorithms, but using survey randoms, or also for the simulation randoms. So when you use a randoms, you calculate the density field with respect to these randoms, and you evaluate on a mesh, 3-dimensional mesh, and the mesh size also determined with respect to the mean tracer number density in survey. And then this density field is smoothed with the Gaussian filter, and the size of the filter is also with respect to mean tracer number density. So basically what you have is the cubic volumes, this cubic size, also called voxels, determined on the density. And then what we do is that how watershed void algorithms work is that you try to adapt. You find the local density minima, which, yes, here, local density minima in the voxels, and then you generate a Bayesian arrangement. And then in comparison to other void finders, we don't do any Bayesian merging. So when we found the local density minimum, we just try to increase it with the next voxel. It is still in the same void. When it starts to decrease again, then we stop there and we define this as a Bayesian. So there is no Bayesian merging. As a result, we find it could be some strange shape. There is no defined shape. and the size can also depend. They are truly under densities with respect to their local region. So the code is available here in GitHub /revolver. We use a revolver code. Yes. And another void finder is a 2D void finder. This is about redshift tomography, defined on tomographic redshift beam. So we project then redshift beams, and we have the galaxy density maps from these redshift beams. Then we find the local minima, and we use circular annuli. This is also described in Sanchez et al. 2016. So we find local density minima and increase the annuli, and when the mean density is equal to the mean density of that redshift slice, we stop there. So this is then we define the void radius. So this is a totally different void finding algorithm than Voxel, and has been used in DS before, and also other lensing cross correlations. So this usually finds the structure elongated along the line of sight, and their radius is much bigger than Voxel, and they are much less in number. So we use a totally different density tracing algorithms, let's say. So I think most of the people are familiar with dark energy survey. Basically, we have a photometric redshift data from roughly 5,000 degrees square survey area. And there's a DCAM is mounted in Chile. So we use DES-Y3 data, but we use updated V054 red magic version. These are low photo Z errors. But this is a big update because we compare our result with previous study and we don't exactly get the same results with them. And that's because since we update the red magic algorithm, both for simulation and data, we have a different void catalog because these galaxy clustering parameters and their colors are also a little bit different in our updated algorithm. And this is the mask. And if you see there are holes in this mask, and one reason to use Voxel void finder that it deals with this survey mask and holes and all the problems much better than the other void finders, for example. That's why we think for future, I think it's an important void finder. So we also calibrate our results based on mice simulation. It's a lambda CDM simulation with these cosmological parameters. This is an embodied simulation. We find the voids, and we have a kappa map in mice. We use that as well. The main difference is the omega m is slightly off from Planck value, but this has been studied in previous papers. In our sensitivity, it doesn't affect results much, but it will affect some. But then we also use an updated error algorithm, which I will talk about. So it will account for that. But in previous studies, it has been shown that we could still compare our results although omega m from mice is slightly low. So on the left is the Planck kappa map, on the right is the mice kappa map. And the first thing we compare is void number density. We find in mice and DES-Y3, and these are the void number density, and they agree very well. So this is our like a consistency check with different types of void finders. And our methodology, we divide Voxel bones into 3 redshift bins with each 3 lambda bins. Lambda is a parameter based on density and void radius. So it's been shown before to cross-correlate with the void gravitational potential. But for 2D voids, we only been on 3 redshift bins because there's no lambda parameter. And what we want to do is a fit. So we apply the same methodology, same void binning in mice and DES-Y3. And this also shows a void size function for voxels. What's important here is that the probability density and the void size is actually agreeing very well with each other. For all of our 9 bins, this is showing for 9 Voxel bins. So we stacked our void positions in my simulation, and then we end up template profiles. One thing is important is that we measure the signal in degrees in theta along the line of in the sky. So we don't do any void rescaling. So the 0 is the void center. And if you see the signal there and low Z, mid Z, high Z, the shape is slightly different. So, and then we apply a match filter from that. And how we drive the match filter, we have a kappa 0 in the center and we have a shape function. Based on this shape function, we create an Hillpix map by applying a univariate spline. And based on Hillpix map, we get the ALM, spherical harmonic coefficients. Basically, we apply an optimal filter that is also make use of Planck power spectrum. We assume that noise has no directional bias. And then we create our match filters, and we cut it in L700. And also for error analysis, we use a jackknife error bar from mice. We use void by void jackknife, but we also tested with different binnings of voids. We found that in our methodology, by using synthetic data vectors with LZ, you can check the paper. Number of jackknife bins actually don't matter. So then we use just void by void jackknife, and we add a random Gaussian noise on it. And then we create this 1000 of this, because that's how we construct our covariance with 1000 kappa map. So these are our results. With 1000 randoms created, we stack DES-Y3 void positions, only central pixels, on this random kappa maps to drive our error bars. And we do the same thing in mice and DES-Y3 for our final results. So here, if you look at that, we do a A-fit. We detect 4.61 sigma from Voxel voids and 2D voids, 5.92 sigma. And this is actually good agreement with lambda CDM prediction. So there is no excess or weak signal. So 2D voids, of course, imprint a little bit higher signal to noise because they're elongated along the line of sight. This is expected. So when we invert it by multiplying with -1 to do the superclusters, we also get 5.94 sigma, similar, but that's also good agreement. So overall, we find a good agreement with lambda CDM, and this is also true when we change the methodology to rescaling our template fitting methodology. We get much lower signal to noise, but we have a good agreement. And these results also agree with Pan-STARRS and BOSS results. So they're also fine. A kappa is 1. So for future studies, I'm going to leave this here. We can expand this with the full sky surveys. We can use another method. So I think I'm running out of time. So let me know if you have any questions in or comments. Yes.